of death and destruction through Paris, France at the time. Although I will say that there's a book written about some of that, and it turns out that a lot of the German officers were engineers, and so they kind of understood these things. They're quite civil about that. Once they got to the IPM, they said, "Hey, what do you guys need? Can what do we need? What resources? Your kilogram is our kilogram. We all work on together on this. So what do you need for that process?" But it could have been random violence that took it out, and even other things like dropping it, in the laboratory. There's a lot of care on this kilogram. It's actually only taken out of the vault for measurement about once every 30 years. What they do is, and it's kind of an interesting ceremony. I wish I had a video of that. There is a video out there on YouTube, but it's kept in the vault, and there are 3 keys that unlock this safe, and they're around the necks of the three scientists that are kind of in charge of this: the International Committee for Weights and Measures, the laboratory director for the International Bureau of Weights and Measures, and I believe the director of the mass metrology section, or key comparison group. And one lives in Australia, one lives up in England. But once a year, they all come together, they go downstairs, they all put their key in the lock, they all turn it, and they open it, and they go, "Yes, the kilogram is still there." And then they shut it. That's how it happens. In fact, it's interesting, the chief scientist in charge of the kilogram sometimes will spend his entire career there in Paris, never getting a chance to even touch the reference kilogram because it's not due for a comparison. But here's the problem that we've had now, is these are the measurements of the international comparisons. So this was when it was originally, the international kilogram was established back here, and it looks like about 1893, I want to say off the top of my head. I'm sorry, I should know that off the top of my head. But you can see here's 1889, here's 1900 on the graph. So every 30 years they were doing a comparison where they would say, "Okay, time for everybody in the world to send back your kilogram," and it's quite the thing. There was a movie made that was a little bit of a Hollywood version of this a few years ago called 1001 Grams, if you get a chance to look it up online. There's a little bit of a scene about transporting the master kilogram from Norway back to the country as well. But you can see out of their comparisons over the years, especially they did a comparison after World War II, and then subsequently, you see what's happening to all of these measurements of the kilograms. So generally, if you look at this, so either every single kilogram in the entire world seems to be gaining some sort of weight in a consistent fashion, or what's the other alternative? Yeah, the master's losing weight, right? We don't know why, we don't know how. Maybe somebody in this room might be doing graduate research and might actually have a better theory. Somebody here may have the leading theory on how that actually happens, because none of us know yet. So that's challenge of science yet to be solved. But the point is we're drifting, and you can see we've drifted upwards close to 50 micrograms on the kilogram. So it's not suitable as a reference standard. We need to change up. We need to tie into a constant of nature. And that's been the challenge for about the last 25 years. And the work is being done at the highest levels as well. So here's how they're going about doing that. So there's been 2 different proposals for a solution for a definition of the kilogram. So one side is called the watt balance, which was first proposed by a gentleman in England by the name of Kibble, and he recently passed away a couple of years ago, so we decided to rename the watt balance the Kibble balance in honor of him, but saying that a watt can be realized mechanically with the present kilogram and electrically with electrical standards based on constants of nature. And I'll explain a little bit deeper how that actually works. So if we could build a precise balance and use the electrical watt, we can probably get to an uncertainty better than the uncertainty associated with the international prototype kilogram. Although I will say, just so we get clear, there is no uncertainty with IPK because it is the kilogram by definition. But you can see there is uncertainty happening that we need to overcome, right? And then the other way that people like Rich Davis from the International Bureau of Weights and Measures, formerly NIST, is atom counting. Hey, wouldn't it be cool if we could count enough atoms and say this number of atoms is a kilogram? That's actually a much more elegant solution, something that's easier to teach grade school kids. But I personally have a little bit of bias against it, and we'll talk about that in a moment when you talk about the real experiments on that. I'm an electrical guy, so primarily an electrical person. But so again, back to the watt balance. So again, we're balancing watt per watt. So we have mechanical watt. A watt is a joule per second, and if you break that down, that means it's a Newton meter over second Newton meter squared seconds, or kilogram meter squared seconds cubed. So you can break it down into those SI units, and you've all done that in your intro to physics classes of how you break down the definitions of newtons and whatnot into our SI units. And then on the electrical side, we could use power equals current times voltage, good old Ohm's law, and the derivation we use on this is V squared over R. And I'll explain why we want to be able to tie to the volt and the ohm, because that works well in our system, as we'll explain in a moment. So how do we get to DC volts? So DC voltage is calibrated or realized today through the Josephson effect. So Brian Josephson was a grad student at Oxford, I believe it was, back in 1968. He mathematically predicted that if you take two superconductors and separate them through an insulative layer, that you'll have quantum tunneling occurring, and when you have quantum tunneling, you'll create a discrete DC voltage in steps of Planck's constant divided by 2 times the fundamental electron constant. So it's either there or it's not. It's quantum in nature, so it's steps. And if we count enough steps, now we can get to a volt. So of course you have to know frequency, and we already said, hey, look, we know frequency way better than anything else. So that's one of the factors in the experiment. We could almost make that down to 0 for its relative uncertainty in this process. So what this is this is an actual computer chip now that we use today. In fact, we use at Fluke, and it's got about 10,700 of these Josephson junctions on the IC. It's made out of niobium oxide, and we put it in a dewar of liquid helium, and then we could get it down to 3 Kelvin. It superconducts around 6 Kelvin, and then we bombard it with about 76 gigahertz approximately, and we get 10 volts out of this chip. And that's how we realize the volt. And our best international intercomparison has been about 0.7 parts per billion. But we recently did a head-to-head comparison with another NIST system, and we compared our DC volt within about a part in 10 to the 10 on that. So Fluke is very, very good. We're one of the world's best measurements in voltage, and this is a picture of our laboratory of our technician operating the Josephson voltage system, and he's been operating that for about 25 years in that particular system. So, resistance, same thing. We could go back to quantum basis. So Klaus von Klitzling won the Nobel Prize in the 80s on this, and again, what he realized is that you could realize this through the quantum Hall effect, where you have a constant called the von Klitzling constant, and you can get the ohm out of the relationship between Planck's constant and the fundamental electron charge squared. So similar to that, and here's a friend of mine, Rand Elmquist at NIST, and he's operating the system down. He's got the nice dewar, big magnetic field applied to realize that Hall effect in the process, just like our conventional Hall effect. But you can see you've got these plateaus and steps that we can count and get back to realize the ohm. So you can see the electrical side's pretty solid. We can get down into parts in 10 to the 9 pretty easy on that process. And again, so this is what the watt balance project looks like. To a couple of different balances. I took this photograph when I was up visiting the National Laboratory of Canada. That's what their balance looks like. It was actually built in England. They experimented with for a few years, and then they moved it to Canada, and Canada took over the experiments. They've done some real world-leading research up there on that. This is the NIST watt balance, a little bit of a different design. We're using a wheel, where this is using a really good knife edge for its process, but and then again the science goes in all the balancing and controlling all the variables inside of that. So, and this is fundamentally how a watt balance works. So what you have is, first, you have two different phases of this experiment. The first is a static experiment where you put a kilogram on one side of the balance, and you want to counteract the force electrically with that. So you want to create a restorative magnetic field of equal force in that process. So on the one side, you have force equals mass times acceleration of gravity. The other side, you have current, and then it also reduces out if you've got a radial magnetic field. You can simplify that equation out to understand the wire length and the flux density in that. So you can, again, realize the electrical side of this equation, and you can get your balance. But those issues about wire length and flux density, we've got to understand those a little bit better and how they behave. So there's a second phase of the experiment where they take the weight off, and then they just let the balance move. So what they're doing in this particular place is they're moving the balance at a specific velocity, at a measured velocity, and they're passing the coil through that magnet. And what happens with that? You induce it. You induce a voltage out of that when you pass a coil through the magnet. So it's equal to negative nu dphi dz out of that. And again, back to the geometry of that same coil that we used in the previous experience, the same length of wire, you get back to the induced voltage equals the flux density times the wire length times the velocity that you're passing that through. So we can measure the velocity really well. We've got nice laser systems that can measure position and speed. So we can measure velocity really, really well out of this process down into parts and 10 to the 9th as well.